Good afternoon. Am I audible? Hello?
Yes, sir, audible.
Okay. Let us wait for like 1 2 minutes so somebody else may join and then we shall start. So we shall be starting in 1 2 minutes. Kindly wait, please. Good afternoon, everyone. Is the screen visible and am I audible? Can you please confirm? Am I audible? Can anyone respond, please? Hello? Am I audible? Am I audible? Is the screen visible? Hello? Okay, okay. Uh, Good afternoon, everyone. I am Adnan Farooq Khan, currently pursuing PhD from IIT Delhi, and as usual, this is the sixth problem solving session for the course Design of Power Electronic Converters, which is being taught by Professor Shabrinath from IIT Guwahati. Like every week, this problem solving session will be from 3 to 5, and it will be on subsequent Sundays. Like this is the 8-week course, and 8-week course, like this is the 6th problem week problem solving session. After that we'll be having 2 more problem solving sessions, and like every problem solving session this week also, I'll be firstly going through what has been taught during this week, give a brief review about what is being taught, and after that I shall be moving towards some problem solving that should help you in your assignments that has been given to you. Coming to this week, in this week mostly what was being taught is about the magnetics, about the design aspect, how to design, how you should design any magnetics like inductor, transformer, and etc. And usually like what was first being taught is like about the fundamentals of the magnetic circuitry and in the magnetics, and after that like different aspect of the losses, magnetic losses, conductors, um, uh, about conductors, materials, and cores. Information was given about that, and was taught like about the different cores that are available to us, different conductors, how to choose them, and if you want to design any particular inductor or so, and how we are going to choose. And after that what was touched about like inductor design, if we have a particular inductor value, and if you want to design the inductor of that value, like how we are going to approach in designing that inductor, and how we are going to do that. That was being taught in this week. As you can see how the course is being progressing, like first we saw about the devices, then their switching, turn on and turn off, then we saw about like the different converters, then how to like choose their devices, then we moved to about like this um, gate drivers and snubbers and all. Then there was about the thermal aspect of this, how to design the heat sinks and all. Now we are moving about the magnetics. If we have an inductor, a transformer in our converter, how we are going to design that. So coming to the magnetic fundamentals, like if you can see here, the basic of the any magnetic circuitry is like a core, uh, a magnetic core. Like this can be of any material, it can be a ferrite, it can be a sand dust, and like different cores are available to us. And what this core does, like if this core has this core allows, like as we know, if we have a current carrying conductor, and this current carrying conductor, that this current carrying conductor has a flux field, magnetic field associated with that. And if we wound this current carrying conductor around the core, as you can see here, a magnetic field intensity is being produced by this current carrying conductor. And what this does is this enables like this. If we have this this current, this generates a magnetic flux. This how we will see how it is done inside the magnetic core. And what is the like idea of why do we need a magnetic core? Because like this magnetic, what you can simply understand this magnetic circuit analogous to an electric circuit. And here you can see that this flux that is being generated by this current carrying conductor is similar to an current as we see in electrical circuit. And this what this magnetic core does is like each of these core will have a permeability of mu. And what we usually see for these different cores, this permeability is very high. That means like it offers a very little resistance to this flux. So what this code does, it provides a path for this magnetic flux to flow, a very low reluctance path there. That means the resistance to the magnetic flux is very low compared to the air, that where this permeability is very less compared to these cores. So if we have a current carrying conductor that is wound around this core, and if we apply the Ampere's law, and we can get a magnetic field intensity H. We know H dot dl, and if we have that, that will be H dot dl. What it will does, it produces an mmf, and that is being given by F here, and that will be equal to Ni, where N is the number of turns of the coil, and I is the current flowing through that coil or a conductor, and that will be equal to H into LC. LC is the mean path length of this core. As you can see here, this dotted line, that mean path length of this core, and H is the magnetic field intensity. So here you can see, if you have a current carrying conductor that is being wound around a core, a flux is being generated that will flow through the core, and this core having the permeability of mu, and core mean length of LC, and having a cross section of AC. And you can see, if we know that mmf that is being generated will be equal to Ni into H into LC. This comes from the Ampere's law. But what we know is, if we know the current, we can calculate the magnetic field intensity, because what is known to us from this equation, what we get, if we multiply this current by N, that will be knowing what are the number of turns that we have wound on the core, and LC will be knowing the mean path of the core, and if we multiply I by N by LC, we'll get the magnetic field intensity that will be generated by this current I. So if we have this magnetic field intensity, after if we have this magnetic field intensity, we can then calculate the magnetic field B, magnetic field density. Just a minute. Then we can calculate this magnetic field density of the core, and if we multiply that this H by mu, where mu is the permeability of the core, which is usually around, like if you take a ferrite, it will be around 2000 to 3000, and it will vary from one core to another core. And if we multiply this mu with H, we will get B. You will have also seen this formula, B is equal to mu H, and this mu will be equal to mu R into mu naught, where this mu R is the relative permeability, and mu naught is the permeability of the free space, which is equal to like 4 pi into 10 raised to minus 7, as you know. And mu R is the relative permeability of this core with respect to the free space. So as you can see here, from this equation, you could see that there is a linear relation between this H, magnetic field intensity, and the magnetic field density. But as you can see, if we increase this H, firstly that there is an increase in B as well, linearly. This is not a linear, but we can approximately as a linear, but after some time vary with the increase in H, there is not much variation in the B. So at this point, what we called it as a saturation point of that. What happens is, like, the magnetic field will be of the free space, and B will be equal to 1. This HS is called as the saturation. This point is this HS, after which, like, the B becomes like a flat curve. This is called as the saturation point. And the relation between this V and H, this varies from material to material. For some, the change in the magnetic field density is sharp compared in one material to another, with the increase in R, as you can see from the two graphs here. So once we got the magnetic field density, we can calculate the flux. We know phi is equal to B into A. If we know the A cross-section area of the core, and we multiply that with the magnetic field density, we'll get the flux. This, as I told earlier, this flux is very much analogous to the current that is in the this electrical circuitry. So if we as you can see this, we have a current carrying conductor, and the direction of this magnetic flux generated by this current carrying conductor wound around the core will be given by the right hand thumb rule. If you can see here, the current is entering in behind like this core. If you apply the right hand thumb rule, you can see the direction of the flux will be downwards. So if you are able to if we know the current that is flowing through the coil, and we know the number of turns and the mean length of the core, which we shall be able to calculate the magnetic field intensity. And if we know the permeability, we can multiply that with this H, and we can get the magnetic field density. And after that, if we multiply that with the core area, we shall be able to get the flux that is flowing through the core. So the core, our main motive is our whole flux should be confined within the core. So in order to in order for that, what we would be wanting is have the core with the high permeability. So higher the permeability, lower will be the reluctance to the core, and this flux will find a path, very low reluctance path through the core, and it will flow through the core. Then if we are able to have this flux, are able to get the flux that will be flowing through the core, then we shall be able to this flux shall link these number of turns with that, and this is called the flux linkage. And it will be this is the fundamental quantity from which we then apply our this we apply this Faraday's law and get the EMF. So this is given by this lambda sort of thing, and it will be equal to n times the phi that is being generated. So if we have the phi, and if we multiply that by the number of the turns of the coil that is being on this on the leg of the core, we'll be getting the flux linkage. So here you can see we have moved from this I. After that, we got the magnetic field intensity. After that, we got the magnetic field density. Then we got the flux, and then we got a flux linkage that will be linking all these number of turns of the coil. This flux will be that will link these coils. It's called the flux linkage. And if we want to have the direct relation, this is no lambda here is not, this is called the flux linkage. Here in the magnetic, it's called the flux linkage that will be linking. You'll subsequently see, I'll talk about that later. So now that will be given by n into phi. So lambda will be equal to n phi. So now if you can see from I, we are able to get this flux linkage. So if we have a multiplying coefficient that will multiply to this I, we should get this lambda. and that multiply coefficient is called as the inductance. So if we multiply this, all these coefficients from here, we'll be getting n square LC divided by mu AC. So if we multiply I by this L, that is given by n square divided by LC divided by mu AC, we will get this flux linkage. So psi will be equal to L into I, where L will be given by n square divided by LC divided by mu AC, where L is the inductance. So this constant value is known as the inductance. So if we have a core where the LC is known, mu is known, and AC is known, and number of turns is known, so we'll get a particular value of L, and for that L into I, we'll get the flux linkage. Here you can see this L is equal to n square divided by LC divided by mu AC. So if you can see here, this quantity LC divided by mu AC is known as the reluctance. This is similar to the resistance. As we see in the resistance, that is given by rho L by A, here the reluctance is given by LC divided by mu AC. So this is the reluctance, that is the resistance offered to the flux by this magnetic core. So what we would want, essentially, if you can see here, R will be equal to LC divided by mu AC. As you can see here, as I earlier told, this mu is higher for the cores, like we have a ferrite core. Let us say we have a ferrite core, we have this mu around like 2000, 3000. That means higher the value of the mu, lower will be the reluctance, and this phi will be confined within the core. So what we would want is, as this value of the mu should be higher, on the higher side, if you compared to the air, where this is equal to 1. Relative permeability of the this compared to the air, which is equal to the 1. So this is known as the inductance. So you saw how we got from, if we have a core on which, like we have a current carrying coil wound on that core, we got how we got an inductance. So if we wanted the inductance of a particular value, we shall be like wounding our coil of a particular number. Then we shall be choosing our cores accordingly to have a particular LC, mu, and AC that we will subsequently see how to go through that process. So once we have a current carrying coil, like we know, if there is a very that as we know, we have a Faraday's law. About Faraday's law, if we have a like a rate of change of, like in the, we have a change in flux or change in current, like what we get a voltage, and EMF will be generated, that will be given by D is equal to d by dt of the this lambda, that is given by the this linkage, uh, flux linkage. And we, as we can see from the previous equation, this flux linkage can be equal to phi into n, or it can be equal to L into I. So by these two equations we can get this that the EMF that will be generated because of this variation in this flux linkage, that will be equal to n d phi by dt, and that will be equal to L di by dt. So if we have a change in the flux or change in the current, an EMF will be getting generated. So this EMF will generate and it will induce a current, and as you have already seen during your courses in higher secondary or in your BTech, you might seen the Lenz's law. So the direction of the current will be as such that it will generate its own flux that will oppose the magnetic field initially that will be generating this flux. That is the Lenz's law, that the induced current will oppose the change in the initial magnetic field that is that initially generates that electric field. So the it will oppose the cause will oppose this the EMF generated will oppose the cause that is causing in the first place the generation of this EMF. So you saw how from like the current carrying coil, like we got an EMF, is generated. That is like, this is essential in when we design a transformer. We have a secondary coil on the secondary side, and we see that we have on the primary side, and we are able to generate the EMF on the secondary side, and they are linked by this flux. So as I told earlier, this magnetic flux, that this magnetic circuits are similar and analogous to the electrical circuit, as you can see here, where this voltage is voltage in the electrical circuit is analogous to the MMF here in the magnetic circuit, which is being given by Ni, that we had already solved, that MMF will be equal to Ni, which will be equal to H into Lc by the Ampere's law. So this will generate a flux, that is, this flux will be analogous to the current in the electrical circuit. And we saw that this magnetic circuitry will have its own reluctance, that will be given by R, that will be given by Lc divided by mu AC. It is analogous to the resistance in the electrical circuit. So here we have a MMF that will generate the flux, and this flux is analogous to the current, and we have a reluctance. As you can saw, higher we have reluctance will be equal to Lc divided by mu AC. Here we have this Lc is the mean length of the core, and AC is the area of cross section of the core, that is given by this gray cross section, and mu is the relative permeability of this core. And higher the value of this mu, and lower will be the value of this reluctance. So here what you saw is like this for a particular core, what we saw is we have this Lc and Ac will be constant. But if we want to change this flux, so the only one way to change is if we want to change this mu, we can change, or how we shall be able to do that so we can get a change in the flux. For that, what will happen, what we do is we introduce a air gap in this code. Just a minute please. So what we do in this code, like we cut a portion of this core, and we introduce an introduce an air gap in this code. So now what we have a MMF that is being generated by the current that is flowing at a number of turns, and we have the reluctance of the core that is given by the RC. Now what we have the reluctance of this air gap as well, that is given by RG. And what we know that this permeability of this core is very high compared to this air gap. So the core reluctance will be very less compared to this air gap. So by introducing a proper air gap, we shall be able to like have a proper have a reluctance which we can choose as our need, and we can change the reluctance of the core. So that is being given, if you can see, the reluctance of the air gap will be given by length of the air gap, which is very small compared to the length of the air core, and will give mu naught into by AC. and RC, reluctance of the core, will be equal to mean length of the core minus the length of the air gap divided by mu R into mu naught into AC, where R is the relative permeability into mu naught. And as I told you, like this, the value of this Lg will be very less compared to the Lc, so we can assume that this will be equal to Lc, so Rc will be equal to Lc divided by mu R in mu naught into AC. But as you can see, as I already told you, like this the value of mu R mu naught is very high compared to this mu naught of the air gap, so the RC is very less compared to this RG, that is the reluctance of the air gap. So we can assume that overall, like the reluctance that is dominant or will be given by this air gap, and like we can approximate that then inductance will be equal to L divided by N square. L will be approximately equal to N square divided by reluctance of the air gap, because like we can assume that reluctance of the core is very less compared to the reluctance of the air gap. So this was about the this was about like introducing the air gap by which we can vary the reluctance of the core, and you can see later on, like there are other aspects in like introducing this air gap, so that we want to like limit the maximum flux density as well, so that will be subsequently taken in the subsequent slides. So here you got the idea about the need to have the air gap. So if you want to like vary the reluctance in the path of the core, we can do that by this introducing this air gap. So this was about the course, and now after that, like the other thing that was introduced about was the magnetic losses. So usually in the magnetics, like we have two main losses, like there will be a winding loss and there will be a core loss. Like as you saw, around the core we had a winding through which the current was flowing, and after like that will have some losses that will be under the winding loss, and we had a core in itself, and in that core itself there will be some losses associated. We'll see what are those losses and how we can calculate those losses. So first coming here is like so in the core losses, like we have the two main losses. In the core loss we have two main losses, like hysteresis loss and eddy current losses. So what is this hysteresis loss? As you know, we have like a varying flux, and that will be having we have a varying like flux density and edge, and that will vary, and what that will cause, usually you can see that this magnetic core will be having will be constructed of that magnetic domains that get magnetizing and demagnetizing. So because of like when we have a like a this magnetizing, it will follow one path, and after the demagnetization of that domains, then the demagnetization will follow some another path, and this magnetizing and demagnetization of the magnetic domains will form a curve of this nature. You can see this B and this sort. This is called a hysteresis curve, and the area under this graph, under this BH curve, that it will give us the hysteresis loss. And this is due to like the magnetization and demagnetization of the magnetic domains, and this can vary for like different core materials, where we can have different core materials which have the different permeability, and different like peak magnetic density, magnetic field density, and so on and so forth. But what is to be known here, that the area under this curve will give us the hysteresis losses. The other losses, as we have can see, other loss is the eddy current losses. And how are these eddy current losses? And as we know, we saw that with the change in the flux or with the change in the current, what we get is like an EMF is generated, and due to that EMF a current will be induced. So if you can see here, this flux is flowing through the this core, and in it itself this phi is changing, and what that will cause inside the core, a small EMFs will generate inside the core, which will cause a small current. So because of that EMF, small currents will flow inside the core, and these currents are known as eddy currents. And because of these currents generated due to the varying flux flowing through the core, these currents inside the core will cause some losses, and these losses are known as the eddy current losses. Yeah, like this is the brief idea I am giving you about this hysteresis and eddy current losses. Like if you want to see into detail, you kindly go through the lectures and or the lecture transcripts, and also you can search about these losses, and you can get the detail about these losses, how these are generated. And here I am just giving you the idea. So now if we like want to calculate these core losses, like these core losses are given calculated by this equation known as the Steinmann's equation, where PC is the total core loss, and this is the K constant, some constant, then F is the frequency, Bm is the peak of the this magnetic field density. So here M and N are the constant that are provided by this manufacturer for a particular material. So here in this equation you can see that I earlier told, like this is the magnetization and demagnetization due to the demagnetization of the domain. Here F is the frequency. So if our frequency is very high, so this will be happening, like magnetization and demagnetization will be happening a number of times. So this will increase our losses, as you can see, where m is some factor. By that factor, this f raised power m, where l will be some constant that will be provided by this. So higher the frequency, more will be the core losses. Also, if we have the higher value of the peak value of the Bm in this curve, if you can see, our core losses will be the core losses will also increase. Also, like this equation will follows very accurately, like if the variation in h is sinusoidal, so this uh, equation gives results very much nearer to the actual value. Then if we, for the other cases, if we want to see the accurate core losses, there are some advanced equations as well by which we calculate these core losses for this inside a core. So after these core losses, the another losses are they like winding losses. So in the winding losses, like there are mainly like DC and AC losses. Like we had seen like we might be having inside the current, we'll be having some DC current as well as the AC current flowing through the wire, and there will be, these wires will have some resistance to these currents, and that will be like the AC and DC resistances. That DC, we know that DC resistance will be given by rho L by A, where L is the length of the wire and A is the area of the wire, and right. And what we also know is, like if we there are some effects that happen in the AC that we know, known as the skin and the proximity effect, that you might have read. Due to these skin and proximity, due to this skin effect, what happens, that effective area of this the conductor decreases because the current is pushed towards the periphery. That is why known as the skin effect. The AC resistance increase is somewhat higher than that of this DC resistance by some fraction, that is given by this FR. And if you want to go into the details of this skin and proximity effects, you can go through these lectures and also search for this skin and the proximity effect. This was about the DC resistance and AC resistance. Now associated with that will be the losses. So for the DC loss, that will be equal to losses in due to the DC current will be equal to DC square into the DC resistance of the winding. And for the AC loss inside the winding, we'll have to calculate the RMS current of RMS current of that will be flowing through the winding, and the loss associated with the AC will be giving root mean square of that current into the AC resistance that we saw will be equal to because of this proximity and skin effect will be higher than this DC resistance. So this was about the losses that will be in the winding. Now we shall see about different types of the windings. So about the winding, different types of winding shall be used. You may see different types of winding that may be used. We can have a single strand wire, as you can see here. If you can see near the arrow that I am pointing, and we can have the multi-strand wires. If the amount of the current that should flow through the current is very high, so the area of cross section of the current area of the cross section of the conductor will increase. So that will itself decrease the resistance to that current. But if for the higher amount of the current, this area of the cross section will get increases, so it becomes very difficult to bend or make a turn of this current. So what we have is we'll having the multi-stranded current, multi-stranded wire. If you can see here in the top right corner, here will be having the multiple strands, and these will be put together and have an insulation, have a common outer insulation. These wire strands won't be insulated from one another, but will be in touch with one another, and they won't be having any insulation between them. And what this will help us in with this, we are able to manipulate our this conductor, we can turn it, make a turn, bend it, and so on and so forth. And the other type of the current is the Litz wire. So as I earlier told you, due to the higher frequencies, there will be some this skin and proximity effect, which will effectively decrease the area of cross section of the conduction. So to avoid that, what we have is this is the Litz wire, where the diameter of the individual wire is comparable to that depth which carries the current, or maybe even smaller than that, so that we can eliminate this the effect of the skin effect. And you can see in case of the Litz wire, these individual strands are insulated, that are put then together put under these casings or the outer insulation. This was about the wire types, and then we'll be having the different sizes, wire gauges, and this wire gauge will depend upon this wire gauge will determine the current carrying capability or the capacity of this of the wire. A particular wire gauge will have a particular wire diameter. So we have a different standards for this wire gauge. One such standard is, like you can see here, AWG, that is known as American Wire Gauge System. So, and other thing is SWG, that is standard wire gauge. So here you can see we have 40 AWG to 18 AWG. Higher the value, that 40 will be having higher the value this of the AWG will be having the smaller diameter, and smaller the area of cross section, that means the higher the resistance. And if we like move like uh, down to this like from 40 to like 0 around towards the 0, like the diameter of this uh, wire increases, like for a particular wire gauge, smaller like the wire gauge number, the higher larger this area of larger the wire diameter, and which will mean the area of cross section is higher, which will mean the resistance offered by that wire will be less compared to the higher wire gauge wire. So for a particular application, if you are able to know what is the amount of current that we have to make flow, and we know the area of we know the wire diameter, we know the current density, then we can choose a particular wire gauge, and then we should be able to like use that in a particular application. In our application, we you shall see how we shall be choosing this wire type. So this was about the wire types. Now moving towards like what are the desirable magnetic material characteristics, that what we want in our magnetic characteristic. So for a particular magnetic material, before choosing a magnetic material, what we look for is like we want a high relative permeability. As I earlier told, like the reluctance has this permeability in the denominator. So higher the relative permeability, lower is the reluctance in the path. Lower the reluctance in the path, that this flux will be confined within the core, and there will be a smaller leakage of this flux, as you will see. And also what we see is like we should have the higher saturation flux density. Also what we look for the core, for a particular core, we should have a higher flux density, like this B flux density should be very high compared to what is our need, because we don't want our core to get saturated, because like if our core if our magnetic flux density is very less, and our core for a particular value of the I current, our core gets saturated, as we saw. After that this relative permeability goes from very high to around 1 compared to the air. If our relative permeability changes, our we saw that L is equal to n square divided by L divided by mu AC. And if you see, L is directly proportional to mu. If our like mu change, so our L will also change, then we can have different parameters in our which can affect our operation of the this operation of this converters also, like that can also sometimes like after the saturation current goes very high, that can itself damage the devices and all. Also the other thing what we look for is the high electrical resistivity. This is the high electrical resistivity of the core. Why so? Because as I earlier told, because of this varying flux, there is a EMF that is getting generated inside this core, and due to that EMF, like these eddy currents flow through the core, and we want to limit these eddy currents as much as possible. And if we are having the high resistivity, these will offer a resistance to these eddy currents, thereby like limiting these losses of eddy current losses. So high Curie temperature. So after this Curie temperature is a temperature after like this magnetic material ceases to behave as a magnetic material. So we want to have this Curie temperature as high as possible, because like after operating this magnetic material at there will be some rise in this the temperature, and that rise should not be higher than that this Curie temperature, because that will affect, because at Curie temperature and magnetic properties of this material will get affected, and if this Curie temperature is very high, so if we have a temperature rise in our core because of the losses inside the core, hysteresis or eddy current losses, still it will be able to function, behave as, have the magnetic properties as we intend it to want, as we want. Also, like what we want is like the low core loss density is like what we always want. Our design is to optimize our devices for the uh, for lower losses, because we want to have the higher efficiency. So what we want to have is like our core should have the lower losses density, like the losses per unit volume should be very less, less. Also, what we want is that our core should be able to operate at higher frequencies at which we intend it to want, like this is also like related to the loss, because we saw with the increase in frequency our core losses increase, and with this core losses there will be a temperature increase as well. So we don't want our temperature to increase beyond a particular point. So we should be able to operate a particular core at a particular frequency that we intend to operate it on, and it should not have a losses, it should not have many losses at that point, so that like our temperature may increase and that may damage uh, so this was about like the characteristics that we want for our magnetic materials. So after that, what we see is we have like different types of the cores. So there are many cores that are available. We can have a toroidal that will be in a circular form. We can have a E core that will be a proper of E shing. There are other there's core. This is known as the ETD core, where we have, if you can see, it will be like an E here, and the central limb will be a circular. As such, it's known as the ETD core. So for a particular core, like these this manufacturer will provide its data, and that will be provided. Like if you can see, what will be first provided, there will be a part number for a particular code, and with that particular code there will be like different dimensional there will be a different data provided for that code. If you can see, the main essential data that is needed is this the dimension of this core. If you can see, it is given like for different dimensions like A, B, E, G, C, and you can see for a particular code, these are provided by the manufacturer, and other things that are provided for a particular code is like different parameters, like what is the weight of the code, what is the mean length per turn that we shall go in the subsequent slides, what is the mean path length of the core, what is the window area of the core, what is the area of the core, or and what is the area product, and so on, what is the kg, and so on and so forth. So if this data is not provided, like these window area, and this can be calculated from these things, like if we have the, if we know this value of the g and we know this length, we can calculate the window area of this code. We can if we know the length of this central limb, and we know the height, we can calculate. If we know the diameter of this center limb and we know the length of it, we can calculate the cross sectional area of this, and we can calculate the length of it as well. So other things can be like deduced from this dimensional statics that is being provided by this manufacturer. So this dimensions part is very essential, that should be provided with this these manufacturer. So as we saw, like there will be many cores and many geometries available. So Then there will be dimensional data and design data that will be provided. And after that, for a particular core, like the other thing that is we have is window utilization factor. What is this window utilization factor? If you can see, there is an E core here. There will be a window, like in that window there will be there we wound on that central limb we want our this wire, and this wire will be inside this window area. So this window area is very essential to know what is the window area and how many turns we can have in that particular window area. So what is being done, like we have a bobbin, like on that bobbin we wound these wires that is being shown here. There will be an n number of turns, and you can see, and each of these wire will have some area, uh, conducting area that will be given by the AW. And you can see this brownish area shows the let us say the conducting or copper area. Around that there will be some insulation, and these insulation will occupy some space. And also, if you can see, if we have like these three layers between these turns, consecutive turns, and between these two layers there will be some gap where we don't have any turn. Also there will be some gap lost because of this bobbin on which like we wound these turns. So you can see here this window is not properly utilized, and there will be, so it is given by a factor known as the window utilization factor, and how much of the window we are utilizing, and it will be given by the ratio of the copper area divided by the total window area. If we know the total window area, and if we know the copper area of this the one strand, and if we know one strand of the wire, and if we know the n number of the strands that we use or number of turns, we can calculate the copper area, that will be n into AW divided by the window area. It will be provided here, window area, in the data sheet, or you can calculate if you know. If we know the length and the width of this window area, you can calculate the window area. And if we like take a ratio of that, and we will get the window utilization factor. Usually this utilization factor is between like 0.4 to 0.6, and we take it that means like the total of zero point 0.4 of the window utilization factor means the 40% of this window is being utilized. This was about the window utilization factor. Now comes another like design aspect which is very necessary, is the area product. Area product is like it is the product of this core area and this window area, AC into WA. So how we will know to calculate this window area, this area product? We saw like we had the linkage flux. Peak linkage flux will be giving into L into I into IL max. That will be the maximum of the current that will be flowing. That will be giving into N phi, and phi we know is equal to B into A. So we got that will be equal to, from that we can calculate the N. Also like we calculated the N, we can calculate from this window area. If we know the window area, we know the area of this wire, and we will be knowing how many turns we shall can be accommodated in a particular window area. From that we can get the N. And if we substitute this N in this equation, we can get Li max will be equal to Ku into Wa AC B peak into AW, where Ku is the window utilization factor, W is the window area, AC is the core core area, B peak is the peak of the magnetic flux density, AW is the area of the conductor. So here we can substitute for the AW, because area of the core, if we know, we can have this current density that will be flowing through the core, what we want, that will be giving with a maximum current that will flow through the that is flowing divided by the area of the conductor. And usually like this magnetic flux this current density is usually in ampere per mm square. And if we substitute this AW in this, we'll get Li max will be equal to Ku into WA AC B peak J divided by IL max. So we know like WA, as I earlier told, area product is the product of window area into the core area, that is given by the WA into AC. It will be equal to Li max square divided by Ku B peak divided by J max. Here you can see Li square is the twice of the energy that it can store. We know the energy storing by an inductor is 1 by 2 Li square. So Li square will be equal to twice of that, and will be divided by so area product will give us the relation between that energy that will be stored in this magnetic circuit, and divided by Ku will be a window utilization factor. B peak will be the peak of the magnetic flux, and Gm will be the current density. So here by this formula we should be able to like calculate the area product. So once we know the area product, so now if we want to design a particular inductance, so what are the like different how we are going to do that, and if we will be provided with a particular design specifications, and if we want to design now our inductor, and now we will see what are the steps that are needed to be followed in order to design a particular inductor or so. So if we have an inductance L that we want to design, and we know that what is the average inductor current that this will be seeing the inductor design using this area product method. So if we know the inductance, and we know the average of the inductor current that is flowing through that inductor, and we know the ripple that is being provided, also the power level is given, and the switching frequency at which we want it to operate. So we can assume, like as I earlier told, the current density of the of wire, usually we take it around like 2 to 5 ampere per mm square, and then we have the operating flux density, this Bm. So we want our operating density to be like slightly lower than the saturation flux density of that core, because we don't want our core to get saturated. Uh, and then we'll be accordingly choosing our core for a particular application, like which can satisfy all our needs, where B is kept in limit, and so on and so forth. And then we have a window utilization factor Ku, as I earlier told, that this is taken around to be around 0.4 to 0.55 or so. And then we have to see for the temperature rise, and because once choosing the core and all, there will be some losses associated with that, and due to those losses there will be some temperature rise, and we have to limit that temperature to under some point, and we don't want our temperature to go beyond that point, because that can have a detrimental effect and damage our circuitry. So in this area product method, so what is the first thing that we have to do? We have to calculate the area product, and we saw the equation for that. We know the L that we want to have, and IL peak, we know the peak current that will be flowing through that inductor, that will be given by the average current into the half of the ripple, because we have the average current and there will be a ripple over it. If we know the ripple and the average current, so peak will be equal to I into delta L by 2 peak, and Ku we know that will be around 0.4. Window utilization factor Bm will be having the maximum that I told you, like for a particular material there will be some peak, and we want our peak flux density below that, and Jm is the current density, and that is usually around 2 to 5 ampere per mm square. So once we know the area product, so we can then we have to select a core. There will be a number of cores that will be available, and what we have to look for is the our core should be the area product of the core that we choose should be equal to or greater than that, because if the area product is less, then it won't be able to handle that amount of the energy, because like it is associated with the energy in a way that core won't be able to handle that amount of energy, and are like it can like that inductor may get damaged or so on and so forth. Once this area product is calculated, like then we can see what is the wire. After that we select the core. After the core selection we select the wire, and we know what is the RMS current that is flowing, and we know the current density. From that we can get the wire area, and for a particular wire area, we can choose a wire of a particular wire gauge. As I earlier told, like higher the gauge wire, smaller the area of the wire, and higher the resistance of that, because like it is inversely proportional to that thing. And once we choose the wire, and after that like we can calculate the number of the turns, and that I told you, and number of turns that we can wound will be given by this KUW by AG, because now we know the window area. After selecting a particular core, we know the window utilization factor around like 0.4, and AW will be given like we have calculated from the wire that we have chosen. So once we got this number of turns, after that like we shall calculate the air gap by this equation that we had earlier seen, where we know now this LG will be given mu A AC n square. We know the number of turns, we know the mu naught, we know the area of the core, we know the length mean path, and from that we will calculate the air gap. So once we have calculated everything, so we need to now do the design check. This design check is to like ensure the design that we have, whatever the design that we have chosen and whatever the core we have chosen, is it fulfilling all our specifications or not. So how to do that? Like one thing is, like first we have to see the peak value of the flux density, because we don't want our peak to exceed the saturation limit. Otherwise our core can get saturated, because our working like flux density should be lower than the saturated flux density. So here, if you can see, take an example of a DC-DC converter. We have a DC current. Over that there will be a AC ripple. So we can have a peak of that like IDC divided by delta L by 2. And if you can see in the BH curve, we will be having some B because of this IDC. Because of that will be given by here BDC. And around that BDC there will be this hysteresis loop because of this AC component, because this AC will cause the magnetization and demagnetization. And this will be around this point BDC. So it will be higher than that BDC. So this peak to peak is given by going to BM, where BM is the maximum point of this flux density. So how we can calculate it? We know that MMF equation, Ni is equal to Hc into Lc. This is of the core and this is of the air gap. And if we can substitute Hc, this will be going to Bc divided by mu into mu naught. For the air gap, it is going to be Bc into mu naught. From that, we will be able to get the Bc, that is equal to mu naught Ni Lg plus Lc divided by this. All these parameters are known to us, and I is also known. So Bm we can calculate by this the peak of the the AC component of the current, and that is like this will be giving a delta IL by 2 from this mean, like this will give us the DC point, and this will give us the peak, and this is delta IL by 2. So because of we can get the this BM point because of that. And what will be the peak? That will be equal to, because of this IDC plus this BM. So we can see, if we know the IDC, we know the delta L by 2, and we substitute in the equation, we get the value of the B peak. And what we have to check for is this peak should be lower than the saturation flux density of this of a particular core that will be provided by the manufacturer. The data of that will be provided by the manufacturer, and we should ensure that it should be below that. So this is the first design check. The other thing is we have to see for is the Once we check this operation flux density, then we have to check for the power loss. So we have, as we have seen earlier, because of this Steinmetz equation we had seen, we can calculate the core losses, and we if we know the IL RMS current that is flowing through the wire, and we know the resistance, what is given is the resistance per unit of this the of the wire, and we first have to calculate the whole resistance of the wire. So if we have the resistance of the unit length, so if we know the length of this one turn, and we know the number of the turns, we can multiply the length of the turn into number of the turns or resistance per unit length, and we can get the resistance of the total wire used. But you can see here uh, uh, the turns that are closer to the central limb on which is wound will have the smaller mean length compared to the second layer and the third layer. So for that, what we choose is the mean length of the turn. We see this is the mean length, and we can it is sort of an average taken in sort of a mean or average of overall lengths. So we assume that the length of the each turn is approximately equal to that, and if we know the length of the one turn, we know the number of the turns, and we know the resistance per unit length, we should be able to calculate the whole resistance of the wire. And once we calculated that, and we should be able to calculate the power loss. And even when these core losses and these power losses are calculated, we have to calculate the temperature rise in the core. So this is given by this equation where P CW is the total core loss, and AT is the area surface area of this core, and this equation will give us the temperature rise, and we want our temperature rise to be below the particular below the Curie temperature, as well as, because if the temperature rise goes beyond the Curie temperature, then our magnetic materials may lose their properties. Also we don't want a very high temperature that can damage our mm, our inductance or make damage our converter. So we want to limit this temperature rise in this, and in this core, if you use a bigger core, like that can have a more surface area, and we can have a AT will be very high, and delta T will be lesser for the larger cores, because of their surface area will be very high, and there will be a more surface to dissipate that amount of the heat, and so on and so forth. So this was about the design checks that you need to take into the consideration, because before designing a particular inductor, so it should follow that. Now we shall move towards the problem solving, and you shall see how if we have to design a particular inductor or so on and so forth, how we are going to do that. So before that, we shall take a break for 5 minutes, like it is 4:14. We shall join back on 4:19, and then we shall take up this problem solving. So coming to the problem solving part, so here what is being told is like we have to design an inductor whose value is like 60 microhenry for a boost converter, and the rating of the inductor is choosing like it should have like a rating of like 18 amps of current should flow through it, and the limit is like 0 0.4 amps, and some specifications are given like maximum flux density should not should is equal to like 0.2 Tesla, and current density is like 3 ampere per mm square. Also the window factor is like 0.4. So now we shall see. So the first thing is like what is being told is to find the area product. Like we saw like how to find the area product. So we saw the equation for the area product is L into IL peak square divided by KU BMJ. So L is known to us, it is like 60 micro. So first thing is like to know is like to have all these uh, parameters in the standard form, like in their SI units, and after that like make the appropriate conversion. So KU is given, BM is given, and JM is given. Like KU is given 0.4, BM is like 0.2 Tesla, which is already in the SI units, and JM is it is given in JM is given into 3 amps per mm square. So we have to calculate it into the SI unit, that is meters, that is equal to 3 into 10 raised power 6 meter amps per meter square, and L is given 60 microhenry, that is 60 into 10 raised per minus 6. Now we have to already the thing is unknown to us is IL peak. So IL peak is for the boost converter is it will have an average value, then there will be a ripple part, and peak will be given by IL into delta IL by 2. So if we know that IL is 18, delta IL is given equal to like 0 0.4 amps, so divided by 2 it will be equal to 18.2 amps. So if we substitute that here, then our area product will come out to equal to 8.281 into 10 raised power minus 8 meter. So but our answer is in the centimeter per raised power 4, so we shall convert back into the centimeter raised power 4, and it will be equal to like 8.28 into centimeter raised power 4. So this is our answer to the question. So area product came out to be, so to have an inductor uh, 60 micro inductor with the current rating of 18 amps and with the ripple of like 0.8 0.4 amps. If we want to design an inductor, we need to have an area product of like 8.28 centimeter raised by 4. So once we got the area product, now what it is saying is that E ferrite core is chosen to design the inductor. It's saying that E ferrite core is chosen. Recall the design data given for E ferrite core in the lecture on the magnetic cores. Choose the part number. So now we have to choose the part number. So if we can see here, the area product that we calculated came out to be equal to AP is equal to 8.28. So as I earlier told, our area product should be at least equal to or slightly greater than this. So if we can see, there are a number of cores that are provided. If you can see the first core, its area product is 0.11, it won't satisfy. Second is 0.314, it is also not, it is like very much far what we want. So if you can see EE625, its area product is like 4.516, which is below the area product that we have calculated. So this won't be able to meet our standards. So the next is E75, which has the area product of 9.433, so which satisfies our requirement. So we'll be choosing an core EE75 core. So the answer to this question is EE75. So the subsequent questions will be based on this EE75 core. So now what it is saying, find the cross-sectional area of the core, mean path length of the core, and what is the window area. So if you can see, we have chosen the EE75. Now what we have to see, AC is the core area. So you can see the core area is 3.370 centimeter square. And mean path length is MPL. If you can see here, M mean path length is 10.70. And what is the window area, WA? Window area is given 2.799 centimeter square. So the answer to these questions were 3.37. centimeter square, 10.70 centimeter, and 2.80, because like we have rounded off here. If you can see 2.799, you can approximately take it around to be equal to 2.80. So once you got these things, now the subsequent questions will be based on these things. Now what it is saying is calculate the RMS current. So the RMS current, as you can see, we have seen in the previous lectures as well. So the RMS current will be given, IL RMS will be given by this IL squared plus delta IL square divided by 12. If you can want to see the derivation of this, like we have discussed this equation in the previous classes, you can go through those slides or the lecture notes. So if we know the IL current, like that is 18, delta IL is known to us. So if we solve this, it comes out to be 18.0004. We can approximate that as 18 amps itself. So the RMS current that is flowing, RMS current for this boost converter is like 18 amps. That is flowing through the inductor will be equal to 18 amps. So now what we have to calculate is the cross section area of the conductor. So we got the current that will be flowing. Also we know also what is given. This J is given to us. It is 3 amps per mm square. So if we know the current density, we know the current that is flowing, we can calculate the area of the cross section. Also like that will be giving about IL RMS divided by J. So here it will come out to be equal to area of the, because we want our answer in mm square, because current was in the amps. This is amps per mm square, so that will get cancelled, and area of this wire came out to be equal to 6 mm square. So now we got the area of the current conductor as well. So we chose our particular this core. Now we have chosen the wire itself. So once we have chosen the wire, we have to see this what AWG we shall choose. AWG to be chosen. So we have seen. So we require an if you can see here the wire area of 6 mm square, and now we have to see this which AWG suffices our need. So if you can see AWG12, as I told you, higher the value of the AWG, smaller is its wire area and higher the resistance per unit length. So if you can see here, AWG12 will have the area of 3.31. Similarly 11 will have 4.17, 10 will have 5.28, and so on and so forth. But if you can see, our requirement is 6. So if we take AWG 9, we have an area of like 6.63. So this should this will like meet our requirements. So any AWG below, like up 9 and below, will suffice our requirements. But with as we go on like decreasing the AWG, our window area, like area of the wire, will increase. But that what we, because of that, since we have already chosen the core, and if we take the higher value of this like area, like then overall number of turns in the window will be limited, because like the cross section area of the wire is increased and we have a limited window area, and in order to full have that certain number of turns in that window area, we shall like choose the wire closest to this window area wire. We should choose the AWG wire gauge closest to this wire area that is being calculated. So the AWG 9 is answer to this question. Answer is 9. So now we have chosen this AWG. Now we have to choose the number of the turns. So we have seen from the equation, n will be equal to the can you please turn off your mic? So n will be given a window utilization factor, window area divided by the AWG. So we have seen the window area for this code to be equal to 2.799, that is equal to 2.8. So window area is 2.8 into 10 raised power. So as I earlier, this was into centimeter. Can you please turn off your mics, please. Turn off your mics, please. So we have to, like, as I earlier told, we have to convert all these parameters into the SI units. So it was given 2.8 into centimeter raised power 4. So we calculated into the meters, that will be equal to 2.8 into 10 raised power minus 4. Also the area of the wire we calculated, it came out to be 6.63 mm square. So we have to calculate that into meters as well. That comes to be 6.63 into 10 raised power minus 6. So if we take the ratio of that, we get around to be 6.89. That is around, like, because we cannot have a fractional turn, so the number of turns that will be, like, used will be equal to 17 turns. So that is the answer to this question. So now what is given is, if the relative permeability is 2300, what we have to do is we have to calculate the air gap length. So we know the air gap length will has the equation Lg is equal to mu naught AC n square L minus LC divided by mu RC. So we know all these, the value of all these things, like mu naught will be equal to 4.10 raised by minus 7. This AC we had seen from the data sheet is equal to 3.37 centimeter square. If we can calculate, convert into the meters square, that is 3.37 10 raised by minus 4, and we calculate to be around 17. LC, we know mean length of the core from the data sheet, that is 10.7 into 10 raised by minus 2 into meters. L is 60 micro and mu RC is given to us. So if we solve this equation, Lg comes out to be 1.99 into 10 raised by minus 3 meters, that is equal to 1.99 millimeters. So the Lg required for this is 1.99 mm. So this was about the questions. I hope, like, this is clear to you, like, how we have designed design a particular if we want to design a particular inductor, how to go through the question. We shall first calculate the area product. From the area product, then like, we shall we can choose from this area product. We shall then choose a particular core. For that particular core, we shall be, like, knowing different parameters, and for that parameters, then we shall calculate the wire that current that will be flowing through the inductor. And if we know the current that is flowing, we can then choose a wire, and by first calculating this area of this wire, and after that by choosing a appropriate wire of a particular gauge and wire gauge, and then we calculate the number of turns, and these turns will be permissible in that thing. And after that, like, we can calculate this air gap as well. And you can, like, then go for the design check as well, that we had discussed in the slides, and see whatever are the requirements, are those met or not. If those not met, then you have to choose for another core which meets these specifications. And that was it for today. If you have any questions, like, you can ask, and if not, then we can close today's session here. And yes, any questions? So if there are not any questions, like, then we can close our session today. I shall be here for some time, like 2-3 minutes. If you want to ask any question, you can ask. I shall be here for 2-3 minutes. If any of you want to ask a question, you can ask the questions. If there are not any question, then we can close today's meeting session here. Thank you everyone for joining and patiently listening. Thank you, everyone.